Hi students, welcome back. Today we are going to continue with the phase equilibrium part 2. Okay, let's begin with non-ideal solutions. So we have negative deviation and positive deviation. Non-ideal solutions is the solution that shows deviation from the Raoult's law. Okay, so first we look at negative deviations. Miscible liquid mixtures are said to show negative deviation from Raoult's law if the total pressure of the liquid mixture is lower than that predicted by Raoult's law. This is ideal solution. So this is a vapor pressure curve. The total vapor pressure of the mixtures will be lower than the ideal. Okay. Since actual vapor pressure is lower than that predicted by Raoult's law, it implies that the tendency of the molecules to escape from the liquid mixture surface is lower compared to the molecules in ideal solutions. This is because the intermolecular forces of attrition between A and B in the liquid mixtures are stronger than the intermolecular forces of attrition between A and A in the pure liquids A and between B and B in pure liquid B. The negative deviation from Raoult's law is caused by the association of molecules or formation of stronger chemical bonds, usually hydrogen bonds. On mixing the two liquids, there is a slight decrease in volume. Heat is decreased. Okay, let's look at the examples of negative deviation from Raoult's law. First, we have hydrogen chloride and water. So between the hydrogen chloride molecules we have weak van der Waals forces. Between the water molecules we have hydrogen bonding. The mixtures will have stronger ionic polar bonds between the two. Okay. The same thing goes to the hydrogen nitrate and water. Hydrogen nitrate also have van der Waals forces. Then the water will form ionic polar bonds with the hydrogen nitrate, which is stronger than the hydrogen bonding and the van der Waals forces. Okay, we have last one is trichloromethanes and the propanones. So trichloromethane has van der Waals forces between them, and propanone also have van der Waals forces between the molecules. But when the two mix together, they will form stronger hydrogen bonding. And for fractional distillation of dilute nitric acid, first we have to understand what is the meaning of azeotropic mixture. Azeotropic mixture also can name as azeotrope is defined as a mixture of two liquids that boils at constant temperature where both the vapor and the liquid mixture have the same composition. In other words, the composition of an azeotropic mixture does not change on distillation because both the vapor and the liquid mixture have the same composition. Let's look at the example of fractional distillation of dilute nitric acid. So the mixture is nitric acid and water. So we have to roll the sketch the boiling point composition diagram for the mixtures. We need the 3 points, okay? Boiling point of hydrogen nitrate negative 78 degrees Celsius, and boiling point of water 100 degrees Celsius. The third point is the boiling point of azeotropic mixture 121 degrees Celsius. Here shows the boiling point composition. So after roll the 3 points, okay, boiling point of water, boiling point of nitric acid, and the boiling point of azeotropic mixtures, we draw the 2 curves. Okay, for vapor is above the liquid curve. Okay, so draw at the section A and section B. For section A, we have dilute nitric acid. The composition of nitric acid is less than 68.2%. For section B, we have more concentrated nitric acid, where the composition of nitric acid is more than 68.2%. Let's look at the section A, where the mole fraction of nitric acid is less than 68.2%. If a mixture of nitric acid water with composition C1 is heated, the mixture will boil at T1 to produce a vapor with composition C2. If this vapor is condensed when coming into contact with the core surface of the fractionating column, the liquid produced will have composition C2 also. When the condensed liquid C2 is in contact with the ascending vapor, it will boil again at T2 to produce a vapor with the composition of C3. If the vapor is condensed, the liquid with composition C3 also is produced. By repeating the process of vaporization, condensation, finally water is distilled at 100 degrees Celsius. And the liquid remaining in the flask becomes richer in nitric acid. The temperature of the liquid mixture in the distillation flask rises during distillation. Finally, when the temperature reaches 1 to 1, okay, we will have azeotrope of 68.2% of nitric acid is distilled out. Hence, the mixture which shows gross negative deviation cannot be separated completely into its pure components by fractional distillation, because we have azeotropic mixture distilled, which consists of 68.2% of nitric acid. Okay, next we look at section B. If a mixture of nitric acid water with composition X1 is heated, the mixture will boil at T3 to produce vapor with composition X2. If this vapor is condensed, the liquid produced will have the same composition X2. When this condensed liquid is boiled again at T4 and produces a vapor with composition of X3. If the vapor is condensed, the liquid produced has a composition of X3 also. By repeating the process of vaporization condensation, finally nitric acid is distilled out at 70 degrees Celsius, the boiling point of the nitric acid. The liquid remaining in the flask becomes richer in water. The temperature of the liquid mixture in the distillation flask rises during distillation. Finally, when the temperature reaches 121, which is the boiling point of azeotrope. Azeotrope of 68.2% of nitric acid is distilled out. Now we look at more positive deviations. Positive deviation and vapor pressure curves. Miscible liquid mixtures are said to show positive deviation from Raoult's law if the total pressure of the liquid mixture is higher than that predicted by Raoult's law. So we will have the total pressure curve above the ideal. Since the actual vapor pressure is higher than that predicted by Raoult's law, it implies that the tendency of the molecules to escape from the liquid mixture surface is higher compared to the molecules in an ideal solution. This is because the intermolecular forces of attraction between A and B in the liquid mixtures are weaker than the intermolecular forces of attraction between A and A in pure liquid A and between B and B in pure liquid B. When the solution of positive deviation is prepared, heat is absorbed and the volume increases slightly. A mixture which shows gross positive deviation, example a benzene-ethanol system or ethanol-water system, the mixture cannot be separated completely into its pure components by fractional distillation. Here shows a positive deviation from Raoult's law. Examples we have ethanol-water system, benzene-ethanol system, benzene-ethanol acid system, and ethanol trichloromethane system. So for Raoult's law, positive deviation from Raoult's law, the mixtures must have weaker bond than the pure liquids. So you can see here, the mixtures of ethanol and water will form weaker intermolecular forces, which is a hydrogen bonds. The mixture just can form one hydrogen per molecule, whereas the pure one, water, can form two hydrogen bonds per molecules. Okay, then we have benzene-ethanol. And the mixtures will have van der Waals forces, which is weaker than the pure ethanol. They have strong hydrogen bonds. Okay, the same things for the third examples, benzene-ethanol acid system. The mixtures will have weak van der Waals forces also, compared to the pure ethanol acids. They have strong hydrogen bond between the molecules. Then last one we have ethanol trichloromethane system. Between these two liquids will form hydrogen bonds, but because of the chlorine atoms here, the hydrogen bond formed is weaker compared to the pure ethanol hydrogen bonds. With the oxygen atom, it will form stronger hydrogen bonds. Let's look at the example of fractional distillation of benzene-ethanol mixture. So we have the information of boiling point of benzene, which is 80 degrees Celsius, boiling point of ethanol 78.5 degrees Celsius, boiling point of azeotropic mixture 67.8 degrees Celsius. So we need to roll these 3 points. Okay, the question: sketch the boiling point composition diagram for benzene ethanol at atmospheric pressure. So here we have boiling point composition curve for benzene ethanol mixture. We have two sections here. Section A, we have less than 32.4% of ethanol. Section B, we have more than 32.4% of ethanol. So this point is the azeotropic mixture point. Okay, next we have to label the boiling point of the ethanol. Okay, here we have 100% ethanol, and boiling point of the benzene 80 here. Okay. So we have Vapour curve above the liquid. Okay. We look at section A first. Section A, we have less than 32.4% of ethanol. So when a mixture of benzene ethanol with composition C1 is heated, the mixture will boil at T1 now, to produce a vapor with composition of C2. If this vapor is condensed, the liquid produced will have composition C2 also. This condensed liquid will boil again at T2, okay, and the vapor liberated will have composition of C3. If the vapor is condensed, the liquid with composition C3 also is produced. So by repeating the process of vaporization, condensation, the first distillate octane is the one with lower boiling point, which is an azeotropic mixture or azeotrop. It consists of 32.4% of ethanol, which distilled out at 67.8 degrees Celsius. And then we have the temperature of the liquid mixtures in the distillation flask rises during distillation. Finally, when the temperature reaches the boiling point of the benzene, so the pure benzene is distilled out. Now we look at section B, which is more than 32.4%. The azeotropic mixture of 32.4% of ethanol has the lowest boiling point. If the mixture of composition X1 is subjected to fractional distillation, the first distillate is azeotropic mixture followed by the ethanol. Okay, now we make comparison of the negative deviation and the positive deviation. We also compare the vapor pressure composition curve and the boiling point composition curve. So you can see here, for the vapor pressure composition curve, negative deviation has a minimum point, okay? Then positive deviation has a maximum point. Okay, for the boiling point composition curve, it will be the opposite, okay, from the vapor pressure. Okay, so negative deviation will have a maximum point at the boiling point composition curve. Positive deviation will have minimum point down. Okay? You always remember that negative deviation, the mixtures will form stronger bonds, so it will have higher boiling point. Okay? So less tendency for the molecules to vaporize, so it will have lower vapor pressure. Okay? So just memorize one. Okay? Positive deviation will be the opposite. Okay? Next we look at fractional distillation of an ethanol-water mixture. The boiling point composition diagram for an ethanol-water mixture show a lowest boiling point at 78.2 degrees Celsius when the mixture contains 95.6% of ethanol. When subjected to distillation, a solution which contains less than 95.6% of ethanol can be separated into an azeotropic mixture followed by pure water. In contrast, a mixture then contain more than 95.6% of ethanol can be separated into azeotropic mixture followed by pure ethanol. This means that we cannot separate pure ethanol from a dilution solution of ethanol by distillation. Pure ethanol can be obtained from the azeotropic mixture by shaking it with calcium oxide followed by distillation. Calcium oxide can absorb the small amount of water in the azeotropic mixture via the following reactions. So you can see the calcium oxide will form calcium hydroxide after reaction water. That's all for the lesson today. If you like this video, please subscribe to my channel and press the notification button for the next video. Thank you.